Hello everyone, this is Basement Builds, and today I will be showing you how I built this robot hand. The hand is an upgraded version of the first one I made 8 months ago. The main feature this video will focus on is the armband, which has sensors that learn from your forearm what you want your hand to do. But first, I'll go over some of the new mechanical improvements. The robot is mechanically pretty similar to the first version in principle. There are 6 motors that control each finger and the folding of the thumb joint. Each motor is connected to a winch which winds up the fishing line, which contracts the finger. The biggest difference up front is that most of the robot is now printed from TPU instead of PLA. TPU is a more rubbery material and is flexible. It's much tougher and more impact resistant than PLA, as you can see here, which is important for making the robot hand more durable and reliable. I even printed the fingers mostly out of TPU, which gets rid of the mechanical joints which were the weak points, although it does require more energy to retract. I also put a big emphasis on repairability for this hand. Each finger can easily be replaced by removing one bolt, and all of the motors and potentiometers are easily accessible. There is some ways to go, however, as if you need to replace a whole wire, you're pretty much cooked. I also moved the motors to the palm and integrated the wrist system into the forearm, which reduced the length by about 45 millimeters and saved about 30 grams. The wrist joint rotates around this metal pipe, which is connected to the hand. The pipe has a ring on it with several detents. The forearm has a spring which pushes on a ball bearing which rides on the detents, allowing the wrist to be stable but rotates with some force. The main mechanical changes I'll be going for in the next version is to also integrate the battery and electronics into the palm, as well as increasing the overall power. This will probably mean bigger or even brushless motors, so fitting everything in this space should be fun. The electrical system is pretty much the same. The position of each motor is measured by a potentiometer, and the motors are controlled by DRV8833 motor drivers. The power comes from a 1500 mAh 2S LiPo battery, and the brain is an ESP32 microcontroller. The only difference is the glove and armband now have their own separate battery and controller. They can now communicate with the hand wirelessly using the ESP-NOW protocol. To understand how the armband works, we'll first take a look at the glove. This glove has 5 flex sensors that control each finger of the robot. At the center of the sensor is a strip of velostat, which is basically a plastic with lots of specks of carbon black embedded in it. When pressure is applied to the sheet, the pieces of carbon get closer to each other. The carbon is electrically conductive, which means that the resistance of the sheet decreases when it's compressed. The velostat is between 2 pieces of copper, making it a variable resistor. If we wire the sensor in series with a constant resistor and apply a voltage across both of them, we can measure the voltage difference between them with a microcontroller, which corresponds to the pressure. Most modern prosthetic hands are controlled by EMG sensors. Basically, a sensor that can measure the electrical signals from muscles is placed on either side of the user's forearm. Then, they can flex their forearm one way or another, which will cause the hand to rotate through a series of pre-programmed hand grips. This method has been in use for many decades now, and while reliable, adds an extra barrier between the user and the hand and makes it harder to control the hand well. More recently, some prosthetic manufacturers have used more EMG sensors placed on the forearm, along with some fancy electronics and algorithms to learn what gesture the user wants to make. This one here is called the Mile Plus system from Autobach and only costs $44,000. I decided to do basically the exact same thing, only using 4 sensors instead of EMG sensors. To do this, the armband needs to do 2 things. First, it has to reliably collect pressure data on the forearm, and second, it has to use that data to predict what hand gesture I'm making. The armband works the same way as the glove, only it has 24 pressure sensors in total. Instead of making 24 individual sensors, it has one large sheet of velostat. On one side of the sheet, there are 8 vertical rows of copper tape, and on the other side, there are 3 rows of tape running horizontally. Each intersection of the copper on each side is a location where the pressure is measured. The horizontal copper strips are each connected to a constant resistor, and the voltages are sampled from the node between the velostat and the constant resistors. The vertical copper strips are each connected to output pins on the microcontroller. Voltage is applied to one row, while the other 7 are connected to ground. The microcontroller loops through each of the 8 rows and reads the voltages of 3 sensors, or one row at a time. Now we have the pressure sensor values at 24 points on our forearm, but we still need a way to figure out what hand gesture we're making based on the sensors. I trained the armband on 4 gestures, those being open, a closed fist, pointing, and a 3-fingered pinch. To do this, I first recorded a few hundred examples of myself making each gesture. To figure out what hand gesture the user is trying to make, We can compare the sensor data to the training examples I collected using the k-nearest neighbors algorithm. This algorithm works by finding the similarity of the new data point to each training example. If we subtract each component of the new data point from the training example, then sum them, we can find a so-called distance between the points. The training example with the lowest distance from the new data point is our nearest neighbor. I used the KNN algorithm with k equals to 1, so whatever category the nearest neighbor is, that will be the gesture that the algorithm will guess we are trying to make. Testing this over 100 examples, the system had a maximum accuracy of about 96%, which is in line with most of the research papers I found in this area. I will be releasing the armband files on GitHub, including a circuit schematic. They should be in the description of this video. I also trained a neural network to do the predictions, which is more of what people think of when you mention AI, but I only managed about 90% accuracy, so I stuck with KNN. For version 3, I plan to collect more data and try the neural network approach again, as it becomes more computationally efficient than KNN as the dataset and complexity grows. That pretty much sums up all the major improvements. The final stats are in, and overall, it came in pretty good. It weighs around 370 grams, costs less than $200, and each finger can apply a maximum force of around 10 newtons. The forearm band had up to 96% accuracy for 4 gestures, although was only tested in one arm position. For the next version, I want to increase the power and make the pattern recognition more reliable for real-world scenarios. If I can double the power while keeping the weight relatively the same, then I think we'll be approaching the stats of the industry standard for prosthetics, which I think would be pretty cool. Thanks for watching. I have some other projects in the works that you're not going to want to miss out on, and hopefully I'll post them in less than 8 months from now. If you like this video, let me know in the comments what you'd like to see me make next.